Okay, so today we have Sahra from the University of Oxford, who's going to be telling us about diffusion.
So hi everyone, I'm Sahra. I'm a third-year PhD student in Oxford, and today I'll be presenting to you the work I did during it, I did in collaboration with an amazing team at DeepMind during an internship this summer. So we will be talking on differential private diffusion models and how they generate useful synthetic images. So first of all, I would like to motivate why we are talking about that today. So generative modeling can be seen as an avenue of private data release. And what I mean by that is that you could imagine a hospital that has access to a lot of patient data, and they would want to share it with the world, but they cannot because of privacy concerns. So they might want to generate a synthetic data set that is released instead. This was, for instance, done in France, where the French data authority, La CNIL, has approved that one hospital actually shares their patient data as a synthetic data set. So they generated some synthetic avatars of each patient, and this was allowed to be shared. And also the British data authority, ICO, has released a PETS guidance last year, where they, for instance, have a chapter on differential privacy, but also one chapter dedicated to synthetic data, where they explain that with synthetic data, you could, by just replacing the real sensitive data set with a synthetic data set, you could, make sure that the private information is not released. However, with synthetic data, there are a lot of failure modes. So it might be that you have a synthetic data set that is supposed to be anonymized, but it actually isn't. So what you need in order to do that is the magical word, the magical term differential privacy. So we can just maybe instead of just generating data with a generative model, for instance, there are GANs or VAEs, diffusion models. We can make these models differentially private and then generate synthetic data with differentially private generative models. And that has been done since, for images, since these generative models exist. But there are a lot of shortcomings. So for instance, there is this huge literature on, this huge literature field on differential private GANs, which are amazing, but there are also changes to these GAN architectures, or even the proposal of completely new architectures that are really special to differential privacy. And they implement architectures that you have never seen outside of privacy. And if you do that, then you cannot profit from the literature that has been going on public image generation and all the open source models and everything that has been going on there. And also, even if you have a model that is supposedly differentially private, often when you have especially when you have special architectures, there are a lot of things that can go wrong. So you can violate differential privacy in multiple ways. For instance, there could be a bug in your code, or there could be a bug in how you evaluate it. Like, for instance, you could train a generative model multiple times and then just release the best one, which is not that differential private anymore. Or just the proof of how you showed that the special architecture was differentially private might have had some mistakes. And even when you have, then imagine you have the differentially private generative model, mostly the literature has limited their evaluations to small image data sets. So they looked at MNIST mostly. There are also works that look at fashion MNIST and a downsampled version of CILAB-A. And one other work that looks at CIFAR-10. But the results there have not been that great, especially when you compare with public models. So here in the bottom right, you see pictures that I've taken from the paper that we will be comparing to throughout this presentation, Harder et al., where they pre-train a special architecture on ImageNet images, and then they fine-tune it on CIFAR-10 images, and they get an FID of 26.8. The FID is an evaluation metric that is often used when you want to analyze how well a generative model is doing in generating images from a data set. And here in the on the left of it, you see images from the denoising diffusion probabilistic diffusion model paper, where they trained a diffusion model on the CIFAR-10 images, and they get an FID of 3.17, which is considerably smaller than 26.8. You also see that these images do not really correspond. Like you cannot, whereas you can see here that there is a horse here, or there is a dog here. These images do not really show you what show realistic images. So we will now do something that every good researcher would do. We just look at the best model that is out there and make it differentially private. So let's look at diffusion models. They have been around a lot lately. So you might have seen all the tweets about stable diffusion or DALL-E 2, where you give it a prompt out of text, and then it generates super realistic images that are high resolution. And this is what we attempt to do. We don't quite get there, but let's see how well we can do and how we can privatize models like that. So first, let me explain how diffusion models work. So diffusion models simulate two Markov chains. So there is the forward Markov chain and the reverse Markov chain. In the forward Markov chain, like in here, we look at the time discrete version of diffusion models. We with each time step add noise from a Gaussian distribution to the images, to like a clean image, until we get a completely noised image. And what diffusion models now do is they parameterize the reverse denoising process. So they try to, for each time step, they try to iteratively reduce the noise that is within the image until they get to a realistic, to the undenoised image. What this means in training is that at each training step, we sample a time step, like a discrete time step, in the interval from 1 to capital T. Capital T is just to kind of stop the Markov chain at some point. So this is often chosen as, for instance, 1000. Then we add noise corresponding to this T. So the larger T is, the more noise we add. To the image x0, which is our completely unnoised image, such that we get xt, which is our noised image. And now we're trying to predict the noise given xt. So we might get like this cat image, and we try to predict how much noise there is in each pixel. And you can do a lot of things with variational inference, or like kind of bounding the log likelihood. But there's also a simple loss objective, which we'll focus on here. So that basically says when you want to train, you just try to minimize the expected error in predicting this noise. Okay, so these diffusion models, as you see, are kind of really stochastic, right? Because you sample the time step, you sample noise, so they should be private. A lot of, like, some papers have recently been put on arXiv where it is shown that this is not true. We will look at two really simple attacks just to show why this might not be the case. So there we sample, we train a diffusion model on CIFAR-10, a public diffusion model, and now we sample images from its trained data set and from a test data set the diffusion model has never seen. And for fixed T, we noise the training images and the test images, and then tell the model to denoise them. And now what you can see is that train images typically have a lower loss when they're denoised, so the model is better in predicting the noise, whereas in test images it might be worse. So MIAM, like membership inference attack, could then just try to distinguish between train and test images based on the reconstruction loss. And if you do that, you can see that for really large time steps, this MIA attacker is actually not as good to differentiate between train and test images, because when you add a lot of noise, then the diffusion model is probably just not likely to reconstruct the image at all. So the loss is too high to distinguish between train and test. If you add really little noise, then the diffusion model can generalize a bit. So it can denoise test images as well as it denoises train images. But for most time step, like especially those smaller than 400, you see that the attacker gets nearly perfect accuracy. So there is some privacy leakage. And in a different attack, you can randomly crop out parts of an image and then tell the diffusion model to impute it. So you do the imputation as similarly to when you sample from the diffusion model. You just add noise to the image and then try to like apply the reverse denoising process. And as you see, on this training image from CIFAR-10, the model completely reconstructs the plane, even though it should not, from the context, it should not know that there was a train inside. So it's probably memorized this training image. So what we now do is we propose to train differential private diffusion models and want to decrease the FID on CIFAR-10 that I've shown you before by more than 50%. So let's do that. On the here in the right corner, you see how some CIFAR-10 images look like. CIFAR-10 has 50,000 images of 32 times 32 pixels from 10 different classes. We pre-train our models on ImageNet. Hardy et al. Also pre-trained on ImageNet. And we here we only look at a different privacy level of epsilon equal to 10. So there are now multiple things that we do that will lead to an improved FID of only 9.8. So we switch the model out. So we first of all use this diffusion model and not the special architecture that was used before. Also, a popular trick in deep learning is to always increase the model size, even though that might not always help with differential privacy. Here, because we pre-trained on ImageNet, it did help. Also, we use huge batch sizes. So just think of a really large batch size and double it, and we probably used more. So we use, I think, 16,000. For CIFAR-10, we used a batch size of 2 to the power of 14, which is about 16,000. Or for Camelyon later on, we used 32,000 as a batch size, which is considerably more than, I think, what, for instance, Stable Diffusion uses, which is like 6 of less than 32. So really large batch sizes. And we also apply a trick called augmentation multiplicity, which was proposed in 2021. So basically, this trick was in a paper on differential private image classification used to change the stochastic gradient descent procedure. So here is just a normal SGD steps. T are the neural network parameters at time step t, and here is your gradient from your loss at observation I, which you then clip before you average it within a batch and before you then noise it. And then the gradient, the noise and clipped and average gradient is then just subtracted from your weights. And this is here the learning rate. So what we do with augmentation multiplicity is we for each image we create augmentations. So here each image has 2 augmentations. This can be obtained by cropping the image, rotating it, or coloring it, just in some augmentation way. And then within each group of augmentations from one image, we just average the gradients before they are clipped and noise and everything. And we do that because this gives more information more information and less variance within this part of the model. So this was already done in image classification before, but what we are doing, we do it for image diffusion. And because diffusion is more complicated, you can do even more things. For instance, usually when you train diffusion models, you have to sample a time step with which you noise your image. So we will also sample the noise for each augmentation. So even without cropping, rotating, coloring, you could still use augmentation multiplicity by just sampling a different time step. And this helps a lot. So as you see, this decreases the FID from 12.7 to 11.4 if you use 256 samples.
One quick question on the slide you presented previously. It wasn't clear to me if you needed to do something like composition or group privacy here because you're forming these examples that are related to each other. Can you elaborate a bit more on this?
So I mean, like so this is the same. Okay, but I just want to make sure that we're talking about the same thing because this image is a little bit misleading. So imagine you have an MNIST image and you just crop it, rotate it. It's like the same image, right? Like it's so when you average it, it's still just one image. You got all the information from just one observation. It's not like you got more observations within this part, right?
Right, and the sensitivity is not impacted because you're clipping after you average. So you're taking all these K things, you average, and then you clip, and that takes care of it.
Exactly.
All right, okay, makes sense. Thank you.
Okay, amazing. Yeah, more questions, please. So yeah, we see that it helps a lot, but also augmentation multiplicity increases the compute you need a lot, so it just makes everything slower, right? Because usually not the whole batch doesn't fit on one device. Usually you have to do something like virtual batching where you just and this is why augmentation multiplicity adds a lot of compute in our case. So we stick to 128 samples, even more you could try more, but also the benefit is incremental after that. So in the last step, to actually get us to an FID of less than 10, we modify the time step sampling. And now we get amazing images. Look at that. So here we see that it is not really obvious what these images could be, or there might not be close to CIFAR-10 images. So for instance, here we obviously see that this is a horse and this is a car. And okay, this might be a plane or a truck, but you see like the images do get better. And now what is this modified time step sampling? So originally the time step is sampled uniformly from 1 to capital T. And that gives us an FID of 11.5. But we saw earlier in the attacks that the attacker is actually not as good for like really small time steps and also not really good for like really large time steps. So we could assume that if we pre-train, for instance, that the model might generalize in small time steps, or that it doesn't maybe fine-tune, the diffusion model is really hard to train for really large time steps and they might not be that important. So because we train these diffusion models because of the differential privacy guarantee, we train them for only 200 steps usually. Here you see that the public diffusion models were trained for like 200,000 steps, 400,000 steps. I think stable diffusion is trained for like millions of steps. We have 200 steps for CIFAR-10. So we want to like focus these steps on the most important part of the time step distribution. So what we do is instead of sampling from the uniform distribution, we sample from a mixture of uniform distributions. So we, for instance, we change the weights to give less weight to the smaller time steps or the larger time steps and focus more on the middle time steps to decrease the FID. We try different combinations. We do that with hyperparameter tuning. And then we see that if we, for CIFAR-10, like ignore the first part and just focus most of the weight on the middle time steps, then we get the lowest FID. And
so, can I ask you a question?
Please do.
What was the FID of the model you pre-trained on ImageNet?
Do you mean on CIFAR-10 or ImageNet?
I guess you use a pre-trained model is like,
Exactly.
guess what?
we-
And what was the FID of the pre-trained model before you did any fine-tuning that you started out with?
Do you mean on, wait, oh, do you mean on CIFAR-10, not on?
I'm imagining that you pre-trained the diffusion model on ImageNet.
Yeah.
And that started out with some FID.
Yeah,
And then you fine-tuned it on CIFAR privately, and then you got the different FID that you're showing us.
exactly.
So what was the FID of the pre-trained model that you started out with?
I don't remember. I'm not sure if Leo Borja remember.
No, I cannot remember. I think it's so like I'm not sure what the number is, but I think it's worth clarifying that here the FID will be measured with respect to the CIFAR data set. So it's probably not that great, but initially before we fine tune it, just don't know the number.
Do you know if it's better or worse than the previous state of the art? Just like does initializing the model on ImageNet already beat the previous state of the art in FID?
I don't think it will, because these are conditional models. So there's a layer you have to randomly initialize anyway. So like when you randomly initialize the conditioning layer after the model is pre-trained on ImageNet, but you replace their previous conditioning with like a 10 class conditioning for CIFAR-10, it's not going to do very well.
What if you just trained the conditioning then?
I think it would do worse, but I don't think we have the number.
I guess the reason why I'm asking is I'm just curious, like, I guess I don't know who else would ask the question, but like, I'm curious, like, how strong the prior is. Like, ImageNet and CIFAR, like, you can train a model on a classifier in ImageNet and get very, like, reasonable accuracy on CIFAR. I'm curious if training a diffusion model on ImageNet is like an exceptionally strong prior and gives you very high.
That is a really good point, and we will talk about this later on again. So maybe we can defer the question for now, because we do not have the exact numbers in the head. But like the training loss does decrease. So there is some training going on. But yeah, please ask it again later. I'll remind you. Does that sound good? Good. Then let us check whether the model is actually differentially private, because we use a budget of epsilon equal to 10. Some people might complain. So we knew that before the synthetic data generator leaked privacy, and now with a differential, like with a budget of epsilon equal to 10, we see that here the curve gets flat, so the mere attacker is not successful anymore. And also when you try to impute this plane image, it doesn't know that there was a plane inside. So differential privacy works, which is great. So this also motivates to look at different privacy levels, where we see if we like had an epsilon of 1, the FID was higher than here. Yeah, the FID at epsilon equal to 1 is higher than the infinite privacy model of Harder et al. But just saying again that Harder et al. Uses special architecture, which is not optimized to work in a public setting, which is why the model performs so bad for really large privacy. Just to compare, like the current state of the art in public image generation is 1.74. Earlier we saw just diffusion models without any tricks. Like this is also a diffusion model, just a really specific one, and a really large one, but like got around 3 points, something larger than 3.1, and we see that we can get up to 7.9 for an epsilon equal to 32. So this is how the images look like with pre-training. I know some people might not like pre-training, so they might say, why don't you do it without pre-training? And that is what is happening without it. So there is a paper that some concurrent work that was released by NVIDIA, where they do differential private diffusion models, and they use similar methodology to ours. And the biggest difference is that they do not pre-train. And here you see that when you don't do that, the diffusion models within the small number of steps or the high noise it has to use cannot learn how to depict objects. Like, it's just everything is a bit like cloudy. So this might be a reason why you would want to pre-train on a public image data set. And now you might not be sure whether our generator, maybe our generator, like one of the reasons why pre-training is also not as bad, is you might say the generator is just learning to generate ImageNet images, right? They might not even be CIFAR-10 images. So what we did is we trained a discriminative classifier on ImageNet and CIFAR-10 training data, and let it learn to differentiate between ImageNet and CIFAR-10, and it got like more than 90%. I think it got like 96% when differentiating between them on the test data. So we use it to evaluate the synthetic data, and here you see that it always classifies it nearly 90% of the images of each class as CIFAR-10 images. So it does learn the distribution shift. But then you might still not be convinced, right? ImageNet and CIFAR-10 are so similar. So we wanted to do something crazy and just fine-tune the model on Camelyon17, which is a completely different data set. So far, I don't know of any differential private image generator that was proposed and was trained on something that is not CIFAR-10, CelebA, FashionMNIST, or MNIST. So we wanted to do something impactful, like a medical task where this is actually really useful. So we trained on Camelyon17, which has around 300,000 images. They're usually 96 times 96 large, but we look at the downsampled version of it, which is 32 times 32 big. They have two labels. These are histopathological images from lymph node tissues, which might depict a tumor or not. So when there is a tumor, you see like everything is further apart, and when you have like these small things, then it's not tumor data. And the special thing about Camelyon17 is that it's part of the WIDES data set, which is on distribution shift. So in the training data set, you have images from 3 different hospitals that use similar staining techniques, which introduces some confounding bias, because in the validation on the test data set, you have different staining techniques. So if you just train a model, like just a pure empirical risk minimizer on this data set, it will overfit and be completely randomly classify the test data. Which is why you have to use something like color augmentation or other tricks to make the model generalize. And here we generated some data. We still pre-trained on ImageNet, but we fine-tuned on Camelyon. We needed more steps because we're fine-tuning on a different data set. So I think we fine-tuned for 300 steps. And you can, if you're not happy with the 32 times 32 resolution, you can also use a black box upsampler, which was, again, this is like a black box that we didn't this is pre-trained on some large natural image data set, and it still helps to upsample this really different medical image data set. And you also see in the pictures already that it kind of learned what the tumor is and what not. So in order to assess whether it actually learned what it's supposed to learn, we trained classifiers. So we trained a classifier on more than 300,000 images generated from our differential private diffusion model. And we saw that it gets 91.91% on the test data set. This is a really, really good score. So a differential private classifier trained with color augmentation just on the real data set got 90.5%. I would say the two models probably perform similarly. This is like, because this is out of distribution shift data, like this is a domain generalization data set, it might happen that the generative model is better than a pure classifier. And the best classifier, so because this is part of the WADS data set, they have a leaderboard. The best classifier on the official leaderboard had 96.5% accuracy on the test data set, but the one on the official leaderboard has, I think, 94% accuracy. So this is actually really good. So we see that the model learns the data distribution of Camelyon17. So I hope I kind of calmed down the pre-training critiques, and it kind of shows that pre-training and this fine-tuning on a completely new domain helps. And yeah, so now that we know that we can generate faithful data, we want to actually show that this is useful. So in synthetic data can be used to replace the full modeling pipeline. So what we want to do is we want to just release the synthetic data and tell everyone to use it without ever looking at the real data again. That is great, because if we use the real data, you would need for each step, every time you use it, whenever you visualize something, whenever you tune, you would just have to add up the differential privacy budget, right? So this is great if it can help. So we already saw that we can visualize the data. You can probably also compute statistics like color statistics and box plots and whatsoever to display those. And what is more interesting is to actually train models, like downstream models on the synthetic data, which is already something we talked about when we talked about Camelyon. So what we do is we train a classifier. Here we train a wide ResNet on the synthetic data set generated from the differential diffusion model and evaluated on the real test set. When Harder et al. Did that, they got 51% accuracy. So just by replacing the model to a better generator, we get, and also replacing the, we also fine-tuned we hyperparameter tuned the classifier more. We got already 75.6% accuracy. Then what we did is on sampling, it gives you better uncertainty quantification and everything, so that also helped. So we just trained 5 different classifiers on the 50,000 data samples and increased the accuracy by that. But also there is no reason why we should limit ourselves to 50,000 samples. The reason why everyone did that is because they say, okay, this is as many samples as we had real data samples, but there is nothing holding you back of just releasing 1 million samples and training on that. And yeah, if you do that, you get like 88% accuracy, which is already better. I think like with pre-training on ImageNet, you can get 99% on CIFAR-10, but usually values around 95% on CIFAR-10 are really representative of state of the art. So we are getting closer. And just to show you that more samples help, you can see here that when you train a single classifier, but also if you have an ensemble of 5 classifiers, the number of synthetic samples always helps, but only if you do not pre-train the classifier. Because you could argue that because we had access to ImageNet data at training time of the diffusion model, we could also use it to pre-train the classifier. So we can do that and get, with an ensemble, we can get 87.8%, which is already really close to the 88% we got before. Here, generating more data did not help. So yeah. And now what is more interesting actually are results we got for something like hyperparameter tuning. So you could imagine that you release the synthetic data set for a Kaggle competition, or just to like external researchers who are supposed to like train models on the synthetic data, and they now train the models on the synthetic samples, and they report you the test accuracy on the synthetic samples, and you want to check whether it kind of correlates with the test accuracy on real samples, and we see it kind of does for different models. Each dot is a model with a different, it's the same model with different hyperparameters. We changed weights, decay parameters, learning rate, and yeah. and the dropout, I think, maybe. So you could also now imagine that you want to retrain the model again once, like, someone else trains it on synthetic samples, tells you which is the best, tells you what the best model was they got, and you train it again on the real samples, and you still want to get the best model that is possible. And here you see that the test accuracy of the models trained on synthetic samples correlates with the same same hyperparameter constellation when trained on the real samples. So this was basically everything we explored in detail, but we also wanted to mention some future work that might be interesting and how these results could be extended. So just to recap, so far most papers have looked at MNIST images. Here are some MNIST images generated from our data set. This is without pre-training. So even without pre-training, we achieved SOTA of 98.6% test accuracy on ImageNet, on MNIST, which is great, right? But also we tried to scale the model more and train it on CIFAR-10 and Camelyon17. Here you see again how large these image data sets are. And you could imagine that there are more data sets here that in the future people might try to do, for instance, ImageNet, with other kinds of pre-training data sets. So what could be potential next steps? Like, these models work great, and we also saw that larger batch sizes and more outmode usually help, but the problem with that is that you just need to train them for way longer, and that might not be in the compute budget. So either you spend more compute to do these things and get better results, or it might be interesting if future research could focus on how to make this training more compute and also sample efficient. And also recently, like, a lot of people have worked on like something like Stable Diffusion. So what makes Stable Diffusion special is that the Stability AI proposed a latent diffusion model architecture where you train like a VQ-VAE or VQ-GAN to encode your high resolution images into a small latent space that captures basically the images. So like, these models are amazing. They reduce the size of the images by like 64, but the images reconstructing them from a small latent space gives you images that were as good as before. So you could use maybe such a, and then latent diffusion models train diffusion models within the latent space of the VQ-VAE or VQ-GAN. So it might be interesting to just use the VQ-GAN and VQ-VAE as they are pre-trained on ImageNet and not fine-tune them anymore, because they also work outside of, they also work with the presence of the distribution shift, and just try to like fine-tune differential private the diffusion model part on the new data distribution. Or like, when you have data sets like Checksbird, they have images from different, like they have lung images from this lung X-rays from the same patient from different views. So how would you want to combine them to achieve something like individual level privacy? And also, another potential step would be to see how these models can be used in different parts of the modeling pipeline. For instance, you could imagine that there are multiple hospitals that all share some data and they want to work together. So how could you use generative models in a federated learning setting to make different hospitals being able to collaborate? Or another setting we thought about was imbalance classification. So you could imagine that there are, for instance, a lot of images already out there, for instance, on with white skin individuals, but there might be some private data set from dark-skinned individuals that you want to augment with. So could you just train on minority classes with differential privacy and release synthetic data samples there? So thank you for listening. That was a presentation of the internship work I did during an internship at DeepMind in the RVAI team. And here are some references. And I also have, I think, like 60 backup slides. Unless someone has questions, then I don't have to present them.
Thank you. A very interesting talk. I'll turn off the recording for questions.